one here you can scan for the joining. I don't like to use Moodle, so I like to use Facebook. It's easy. Okay. So this is the course of design optimization. I'm Paul Lee. I'm the professor for the course. Okay, so I will be using Facebook for sharing the information of the course. And also, my TA will post same information on Moodle, but I don't use Moodle myself. I don't use Moodle. So if you message me on Moodle, I won't reply to you. So this semester's TA is my PhD student, Tajil. Can you? Yeah, she's the TA. Okay. So if later on you have questions, you can ask her. And there's a web page on my lab's web page. If you go there, okay, there's a list of all kinds of courses that I have taught with online information, and optimization is right here. So I have taught this optimization, graduate level optimization course for several semesters. So the course material is almost the same every semester, but sometimes I change a little bit. So the reason why I put the online information on the web page is for you to review information in different years. If you cannot, if, for example, if one semester the video was not recorded perfectly, you can always go back to other old semesters and find the same topic. And maybe in a specific semester I explain something better than others, then you can always check on them. Okay? So, this is the web page. And we need to have a discussion about the entire semester. This is just initial layout of the syllabus from the previous semester, but now I will need to check if there's a conflict with some other events. So today, do we do some grouping, right? Maybe we do the grouping next time, because some of you, maybe some others will be joining us next week. So let's do grouping next week. Okay, so today I will be introduced optimization, but also I need to check about this semester. So when is the midterm week? Let's see. I know March 3rd is a holiday. Okay, and then April 7th is the midterm week. Okay. June 2nd. Okay, June 2nd is the final exam week. Okay, so yeah, today I will talk about introduction to optimization. Next week I will talk about so-called unconstrained optimization, starting from a very fundamental method called Newton's method. Since we will have 1 week being skipped, so I may need to talk more in the next week, or I will start to talk about Newton's method today, so that I can make up some of the missing lectures on the 3rd week. And these are fine. I will talk about those. Skippy's descent, conjugate gradient, and then constraint optimization, linear programming, and I will do KKT and quadratic programming. Okay. And then I will get rid of these. I think after the midterm, we can do proposal already. And then I will talk about evolutionary optimization, genetic algorithm. Okay? And then we have several weeks. I will talk about some special optimization problems. Such as multi-objective and I think I will do a multi-objective and also collaborative. And then special optimization problems, optimization with uncertainties. And then maybe I will do a progress report, and then special optimization problems, optimization in AI. And the last week, probably I would say So in the final exam week, we will do, or we can just have final presentation before the final exam week. So on the final exam week, you can focus on your exams. So this could be your final presentation. Maybe that's not good because we already missed 1 week. So I guess we have to do the final presentation on the last week. I think that's better. And a week later, deadline for submitting all files of final project, all project files. Okay, and right here probably just a topic to be determined. Okay. So we will have one backup week on the May 26th. So if maybe our progress was slow, or if something that draws some of your attention, we can use that week for the lecture. Okay, so I don't have any special meetings for Mondays this semester, so I won't be modifying the syllabus too much. Okay, let's talk about homeworks. Nowadays, I'm not sure if you need to do homeworks because ChatGPT is so powerful. It can complete the homework for you so easily. But we need to have exams. I forgot to put exams. I actually want to pay more attention on lectures. I want to spend more time on sharing more information with you, and even do some programming, some coding right after the lecture, so you can directly learn from what was taught in the lecture. But what do we do for the exams? Can we just do one exam? So just midterm at midterm week. Are you guys okay? So just one exam. So if you are not doing well, then you may drop it. Okay, so if we have an exam right here, then I will tell you what will be covered. Newton's method, Stevie's descent, conjugate gradient, linear programming, and also KKT. So this is Stevie's descent, conjugate gradient, linear programming. Okay, so I will only ask you to solve problems by these 5 different methods. For the rest, it's too time consuming for you to write down something in the answer sheet. So anything that is later than quadratic programming, in the future you basically learn by yourself. I don't have any exams for it. Okay? So one exam. I can still give you homeworks, but I'm not going to grade it. Are you guys okay? So basically in that case, I will just, in the past, I give homeworks and then I will say, okay, there's some number that depends on last digit of your student ID. So everyone needs to apply your personal numbering to the problem. So everyone needs to solve a different problem with different numbers. But that gives the TA a lot of trouble because the TA has to solve the same problem 10 times with numbers from 0 to 9. So it's very time consuming, and nowadays you can just easily solve it with AI. And I feel like in nowadays learning, it makes no sense to give homework anymore. So I will just give you a problem. There's no secret numbers. I will tell you, okay, this is a problem for you to practice. I will show you the solution process. Maybe ChatGPT show you a different solution process, both works, okay? And then you can use it for your own practice. You can practice in your own way. You can repeat what has been done. You can solve it by yourself and then check with the answer. So it's just for you to practice, okay? So no homework assignments. Now we need to talk about grading. Since we change a lot, so the project score, the proposal, if the proposal score, let me see, delete this. If this is 10 points, progress report 10 points, final presentation, let's say 30 points, that would be 50. And let's have a midterm of 40. So in total, that's 90. And your attendance will be 10 points. So we will start to collect the attendance points from next week. So this is one. So every week you will get 1 point if you participate in the lecture and check in. Let's see how many in total. Hey, exactly 100. So magical. Okay, great. Okay, so starting from next week, we will do the attendance check. Every time you come, you get 1 point. Okay, that's the easiest 10 point you can get. And I will say the most difficult point you can get is the midterm, because I cannot guarantee how hard you study for the exam. And every time I will give you homework, the exams will be similar style, just like the homework. Different numbers, different ways of describing similar solution process. Okay, so that's for the syllabus and the scoring. Now let's talk about project. So let me see how many students we have. Something like 25. Okay. I know there are around maybe 7 of my students, 7 or 8. So I hope my students can be separated into different groups. Okay. So later on for the grouping, next week, I will count how many students I have. Let's say 8. Then we have 8 groups. So none of my students can work together. So it will be fair to others. So every one of you will be working with at least one of my students. And they are just a master first year student, so they are not good in optimization as well. But I don't want them to, get together and just team up like against each other. Okay. Anyway, so let's say we have 8 groups in the end. Then I will, through the lectures, I will guide you to the projects. I will let you know, okay, what kind of topic that you can choose for your final project. I know, okay, let me check which division you are from. Who is from solid mechanics division? Solid mechanics. Li. Solid mechanics. Raise your hand. Solid mechanics. Okay. Who is from thermal? Anyone from thermal? Who is from manufacturing division? Okay. Who is from control? Okay. So who is from material? Okay. What happened to the one who didn't raise your hand? How about you? I didn't see you raise your hand. Okay. So anyway, we don't have thermal. But some of you are from different fields. So who is an undergraduate student? Okay, undergraduate. Okay. Who is PhD student? Okay, only 3. So for the master students, who is already in the second year master? So good. So all of you are the first year master. So you must be working on some research topic with your advisor. It's okay to bring your own research to this project, but later on, we need to think about copyright issue. Because I don't want this project to become an issue in the future. So let me use because let's say there's one of my students, so Ho-Ting Lin student, okay? And let's say there's another student, for example, Professor X student, right? And maybe another Professor Y student. And you guys become a team and choose a research topic for the project. And optimization is basically a mathematics skill, so it has no copyright. But you may want to apply the skill to some problem. So let's say this student decided to contribute on the idea, and he said, okay, let's focus on, for example, a manufacturing process. Okay, and basically for the topic, you guys are doing some optimization to for the process, right? But later on, when you proceed to build some model, you need data, and the data came from this Professor X student. So then there's an issue of copyright. Whenever a group decides to contribute on the project with your lab's resources, all kinds of resources, let me know, and then I will ask this Professor X, can this group of students do this and do that? If the person approves, then you guys can do it. And later on, if there is a potential publication, because you know, whatever we're doing probably can be published. Maybe we can submit to a conference in Taiwan, which doesn't cost too much. I cannot bring too many students to a conference outside of Taiwan, too costly. But maybe somewhere in Taiwan, because we have a lot of conferences in Taiwan. And maybe that whatever work you have done is really suitable for publishing in a conference. And we can try to do that. But when we do that, then we need to acknowledge whoever contribute to the publication. So the authors will be the students, and also the advisors. Because especially for Professor X, if his lab contribute in the data that is required for this paper, definitely his name has to be included in the author. So the professors. And also whoever that is necessary for the publication. And if we really push one or some of the projects to a conference, I will discuss with those professors and see how who would be interested in pushing this, making this work. Usually in the previous years, usually they will just say, okay, agree, but they won't just spend extra effort on making this work. So usually I'm the person who makes this paper be published. So usually I will pay for the registration fees and also some of the travel fees for the student who is going to be presenting in the conference. But I will not cover for every group's project, because usually I will check, okay, oh, this one is good, then I will just privately discuss with the group. And in the past, some groups will refuse to do extra work because they just treat this as a course. When it's done, they don't want to do more. They got the credit. That's totally fine. Okay, so these are just possible extended achievements that we can collect together. If some of you do a good job at the end of the semester. So just for you to know, we do have some previous students who published some papers with me at the end of the semester, and we got agreements from their professors. Okay? So that's what I want to tell you about the project. Now these are just these are the old rules. I will remove this and I will create new ones later on. Okay. Are these the students for this semester? Okay. So later on, after I finish, I will check with every one of you, and if your name is not here, you can come here to type in your personal information. And of course, next week we can, and also you need the code for adding the course. The TA will help you to get the code. Okay, so everyone here can join the course if you want, so no worries. Now, let me see if I can use my iPad. Okay. I'm sorry, this is very bad. not working. So I think I will use the ball. That's the only way. Oh, sorry. Okay. Okay. Now, let's use the old-fashioned way of teaching. I enjoy using the board or iPad to give lectures. So I will do some handwriting. But when I do some handwriting in English, sometimes it's quite fast. So you may not recognize what one character I was writing. So I will write down the characters how I usually write in English, and you can learn how my handwriting looks like. Sometimes it's like this, sometimes it's like this, Q sometimes like this, O sometimes like this, sometimes N and N. What else? Yeah, for the capitalized character, it's easier, but for the small case, so R and S are just harder to recognize sometimes. So for example, I optimization. So this is Z. Right? So you need to recognize those words. So let me tell you a story. When I was a master student, I took a course, I think it's in solid mechanics, advanced solid mechanics. And my advisor, I think he is from Egypt or some country, I forget. And his handwriting was is sloppier than mine, okay. And I think it was in the first class, he wrote a word, the English word. I have no idea what the word is about. It's like a drawing. So at the time, I decided to exactly copy the drawing of that word, but I have no idea what the word is about. In that entire semester, that word is a mystery for me. I have no idea what that word is about, but it doesn't affect how I learned the course. And 2 years later, I need to review the same course for my PhD qualified exam. In my school, Rutgers, it's not in the same style. We need to apply, okay, I want to do qualified exam this semester. And then on one day, they will give you, it's a 3-hour exam, and you go into the room. It's actually a 3-hour exam for 3 subjects. So 1 hour per subject. They give you 3 pieces of papers, the question sheets, 3 pieces, and then each for each subject, of course. And they give you unlimited amount of solution sheets. You can take as many as you want. They give you 3 hours, and then you need to solve the exams for 3 subjects. So that's 1 day. On the second day, again, so totally 6 subjects in 2 connecting dates. So it's very intense, very difficult, and if you fail, you can no longer study for the degree. You need to go back home. So we studied very hard. And when I went to USA for the master, I took the course, and I kept the notes very carefully because I know later on if I study for PhD, I need my notes for the qualified exam. So 2 years later, I reviewed the notes, and what surprised me was that mystery drawing of that word become recognizable. Because when I first went to USA, the writing was everyone's writing is too sloppy. I couldn't recognize it. But after 2 years of experiencing American culture and reading all kinds of handwriting, that picture become recognizable. So that's how I just an experience of my journey in USA. Okay, so let's get back to optimization. Okay, so it's not very. There are 2 major things in optimization. So usually in an optimization problem, you need to describe the problem. So an optimization problem, okay? You need to describe it. There are many ways to describe it, but there is a very common way of describing it, a very general way. So mini-mine, I will show you the most common way, and I will let you know what those means. Okay. And this is a very, very common way of describing an optimization problem. But if you have never learned about optimization, you may not understand what's going on. So let me explain what's happened. This one is called the objective function. And these are the constraint functions. And x is your design variable. Okay? And what does ST mean? ST means subject to. What does subject to mean? It's like a limited by. Limited by or constrained by. And for Taiwanese, if you really need to know, it's like a 受限于. Okay, then for Taiwanese kids, you guys are okay. So ST is not such that. Okay, not such that. Okay, it's subject to. Okay, usually there is a kind of action right here. It's like a key action, main action in optimization. So optimization is like an action. You need to do something. And usually this is where you write down what you want to do. You basically want to minimize f. So min means minimize. So under the constraints of these functions under these rules, minimize them. Okay? So how, if you are writing a research paper, how do you describe this? You can say, this optimization problem is to minimize f. You can even say n subject to two constraint functions. And sometimes when we say what are the control variables, design variables, we will use the word with respect to. X. So in research paper, you can say a word like this. You can say a sentence like this. There's an optimization. It describes what you're going to do. And I do see sometimes people just write down this sentence, but doesn't clearly describe how the problem looks like. Because maybe the paper is not about making this so clear. But usually, this formulation is written. So sometimes we call this a problem formulation. Okay? Okay. And from here you can tell, for the constraint functions, there are two different kinds. For the G functions, we call them inequality constraints. And this is equality constraints. So, what's the difference? This is equality sign. This is inequality sign. They are different. They are different. Okay? Inequality. Equality. 等式不等式. Mathematically very different. Okay? So I can give you one example. Can someone tells me what is the solution for this? So when x equals to what? F is minimized. It's very easy. Anyone? Anyone volunteer? Okay.
0.
Yeah, very easy, right? So basically, how do we write down the answer in optimization? We usually say X star. So the star means optimal. Optimal solution. And we can even have F star. Sometimes people do that. Or basically the answer will be plug in 0, so 1. So F star, the smallest possible value for this very simple problem is here. When x equals to 0, the object function equals to 1. Okay? How about another problem? Anyone? What's the solution? Yeah. Because if x equals to 0.9, it violates the constraint. If x equals to 1.1, the objective function value will be larger than the value from x equals to 1. So by try to plug in some numbers, possible numbers, to this formulation, you realize only when x equals to 1, the objective function value is the smallest. And also, at the same time, satisfying the constraint. So we usually say satisfies the constraint or violates the constraint. Okay? So the solution for this one, x star equals to 1, and the objective function equals to 2. Right? So now you know a little bit about optimization. So what is this course about? This course will show you some optimization problems which may not be easy for you to visualize a solution so easily. And there's a solution process. There are tons of algorithms suggest you what you can do so that you can explore the design space and find the solution more effective. So let me show you more terminologies about optimization. So usually when you have a problem like this, x should be a real number, right? But we didn't define so precisely like mathematicians. But when you do that, basically the entire real number space is your design space. You can try to find a design in the entire space. You can specifically change the space, but you need to define properly. Otherwise, when people see this, they don't see this, they just assume, okay, you are trying to find a solution in the real number space. Okay? But in the design space, some solutions satisfy the constraints. Others violate. So we will call the ones that satisfy the constraint the feasible design. Or infeasible design. So for Taiwanese, what is feasible? Feasible is 可行. Infeasible is 不可行. So what does that mean? If you have a solution that is feasible, that the design satisfy the constraint. Okay? If it's infeasible, then violates. Okay? So when we are trying to solve for the optimal solution, we try to avoid infeasible design space. Try to avoid it. We want to stay inside the feasible space. So it's like a puzzle, and there is a treasure inside the puzzle. It's like you are trying to find the puzzle. find the treasure. But you don't want to bump into the wall, penetrating through the wall and get out of the puzzle. You want to stay inside the puzzle. So the constraint is like defining the path, but you need to explore it by yourself. And the stupidest way to find the treasure is to find everywhere. That's the stupidest way. Optimization methods try to help you along the way with some information of the process. The method will introduce some effective suggestion for you to decide where to go for the next step. Okay, so design space, feasible design, feasible design. And the level of, or I can say there's a term called feasibility. This term is like the level of your design, whether it's feasible or not. So sometimes in this field, people will say we want to keep the feasibility. That means you want to make sure your design remains feasible. Okay. There's a term like this. And they want to, there's another term for objective function called optimality. Optimality. It's like you try to reach the optimality. So if you have a design that is keeping the feasibility and also having the optimality, that means that's the optimal solution. So sometimes you see people talk about these two terms inside research papers. So if it's a design that is not optimal, not the best design, then it's not having the optimality. If there's a design that is not satisfying the constraint, then it's not keeping the feasibility. Okay, so those are the terminologies. Okay, and I will give you one example of how the optimization problem look like, and inside the process you will see some important steps. Okay, so that will be the method I will be introducing the next. So I want to introduce one-dimensional, basically 1D, Newton's method. Okay, and I think I will prove the equation next week. But there's an equation. I will show you the solution process. Okay, and with this solution process, I can introduce some terminologies to it. So there's something called initial design or initial guess. Okay. So initially, you need to make a guess of your solution. So usually, we have a number that represents different versions of your design. So initially, we usually say k equals to 0. So what is k? K is called the iteration number. So what is iteration? It's like different times of your solution exploring. Every time you explore one spot inside the puzzle, that counts as one iteration. Okay, you move to here. Did you see the treasure? No? Okay, let's apply some methodology and it tells me, okay, go to here, second time. So that would be a second iteration. So you will be keep on doing this until you find the treasure. So in Chinese, it's called 迭代. But in, there's no other explanation for English. But for Taiwanese, when they see the words, oh, iteration is this. So initially you have a guess. So let's just solve a problem. Minimizing 3x squared minus 4x. Okay, very simple problem. But you can solve it by hand. But let's use Newton's method. And let's have an initial guess. For example, 2. Okay. Now, so initially k equals to 0. Initially k equals to 0. So for the solution process, for Newton's method, what you need to do next would be solving for f prime and f double prime, and you need to plug in xk. Okay, so if I need this, I will just derive f prime will be 6x minus 4, f double prime is 6. Okay, so those are the basic information that I need for the optimization process. So over here, I just plug in, so 6 times 2 minus 4, here this is 6. Okay, so this is what I need for applying the Newton's method equation. So what is Newton's method equation? Tells me xk plus 1 equals to xk minus f prime of xk over f double prime of xk. Okay? And so let's just truly plug in. Xk equals to 2 minus, over here, this is 8. So minus 8 over 6. So this is 4 over 3. So this is 2 over 3. Right? 2 over 3. And in optimization, what you need to do next is to do something called convergence check. Check if the solution process is converged. And over here, usually you need something called the termination criteria. Criteria or criterion. It depends on how many you have. Let's just say criteria. Okay. And usually you can make your own decision about how you want to define convergence. So over here I will say if the new solution minus the previous solution is smaller than a very small number, if this satisfied, then converge. Okay? So that's my criteria for convergence. So if yes, converged, then my optimal solution equals to the latest solution, the last one. But if not yet, what if not yet? What if not converged yet? We need to go back to this particular stage, but also k equals to k plus 1. So you will advance the iteration number by 1. Okay? And you repeat this process until you satisfy the termination criteria. So yes, they converge. Okay? So let's, based on what I have done here, let's check on the termination criteria. My new solution is 2 over 3. My initial guess is 2. So if I plug in 2 2/3 minus 2, it's not a small number, definitely larger than 10 to the power of negative 3. So not converged. So if it's not converged, I need to move on to here. And now my k originally was 0, now k equals to 1. So I need to do the second iteration. So initially it's called the first iteration, right? Or where k equals to 0. The first iteration tells me a new solution, which is x1. Initially, I have a x0. The first iteration gives me x1. I checked whether x1 is very close to x0. Not yet, so I come back and I advance my iteration number k by 1. So now my k equals to 1. So in the next process, you will be doing the same thing with the information of x1, you will get x2. And you will come here and check again until you realize converged, then stop. Okay, so let's do the second iteration. So for the second iteration, f prime of x1 plug in. So over here, when I come here, k is becoming 1. So plug into this equation, this is f prime of x1. So that will be 6 times the previous solution, 2/3 minus 4. So that's 0, right? And the f double prime of x1 is still 6. So in the second iteration, x of 2 equals to x of 1 minus f prime of x1 over f double prime of x1. You realize the answer will be 2/3 minus 0/6. So the solution is still 2/3. So when you move on to the convergence check, you realize you're comparing 2/3 and 2/3. Definitely 0. Definitely smaller than 10 to the power of negative 3. So converged. Okay? So the solution tells me the answer is x1, x2, and x2 equals to 2/3. So from here, you realize that the entire process doesn't care about how this function looks like. You never try to do some kind of analysis on the function itself. Like if in high school, if we try to solve that problem, we may want to modify the form of this equation into a certain form so we can observe where is the minimum point. But in the Newton's method process, you realize you just rely on certain equation. This is and usually there's a proof. How come this equation brings your current solution to a next solution? And how come that next solution reaches optimality and feasibility more than the previous one? So usually there's a proof. So in this course, I will be introducing you with many different kinds of methodologies for different kinds of problems. And then we will exercise on the board, and then I will even do some coding for it. Okay, so that's basically what I want to cover for today. Just give you a little taste of optimization. And Meanwhile, learn some of the terminologies. Okay, let me review what has been given to you. A optimization problem has an action, usually minimize. You can maximize it, but usually minimize. Because all the algorithms have been derived based on minimizing problems. So if you try to solve the problem with the action of maximizing, all the algorithms need to have a negative sign. So it's troublesome. So the mathematician decide, whenever we solve optimization, let's do minimize. Okay, so usually minimizing, and if you want to do maximize, for example, you want to maximize negative x to the second plus 6. If you want to maximize this is equivalent to minimize having a negative sign in front of it. Because if you want to maximize the function, that is equivalent to minimizing the negative value of that function. So in the future, let's say you want to maximize profit. You can minimize negative profit. So you can still use all the mathematical tools that we have learned. Okay, so there's an action of minimizing some kind of function with respect to some design variable, but meanwhile, there are some constraints that the process is limited. So you have two kinds of constraints, one with an inequality sign, the other one with equality sign. They are called the inequality constraint and the equality constraint. And you try to explore the design space. Some part is feasible, some part is infeasible. So for the feasible designs, they satisfy constraint, but not every one of them is optimal. They're just feasible designs, they are just satisfying the constraint. They're safe designs, but not the best. For the infeasible designs, they violate the constraint. It's like a dangerous design, violating the rules. Definitely not the solution. Okay? And if you find a solution, you put a star sign at the superscript of the variable to indicate that's the optimal. Okay? And inside the optimization process, usually you start with some initial guess. And you will usually, most methods has iteration process. You will have a initial iteration number, usually starts with 0, and then you have a initial guess. So you will be doing some kind of process. This is for Newton's method. For different methods, they have different process. But usually the method tells you what to do for the next iteration, or for the next solution. So you usually plug in the current solution point. It tells you what to do for the next move. That completes that iteration. Okay, and then after finding the next point, you will need to check whether it's converged. There are many ways to define your termination criteria. This is just one example. If you say, okay, I'm satisfied, then converged. If not yet, okay, go back. Go back to here. But when you go back, your iteration number increased by 1, and then you will be repeating this until everything finishes. Okay, so that's for today. We still have a lot of time. I think we can work on the student list. So I will be showing you who's already in the system. If you are not in the system, you can come here and type in your student ID and your name. And if any of you want to drop, please let us know you are dropping. Okay? So here are the ones that are already in the system. Okay? So if you are not in the system yet, you can come here and write down your name. We need to give them the SS code. So the TA has a bunch of SS code. You can take a picture of the code. So let's do that now, and I will stay here for 10 minutes, 5 or 10 minutes, just to make sure everyone's okay. That's it for today. Thank you. So let's start to do this.